Hey,
Hello.
hey, how's it going?
Good.
Getting ready?
Yeah, I'm gonna have to put you all as co-hosts so that you can like unmute yourselves.
Sounds good. Hey, Gene,
Hey, Barhano.
how's it going?
Good, good. How are you? You looks good.
Yeah, not bad.
It's
Well,
it's been a while.
Yeah.
yeah. How's how's life in Georgia?
Um, it's so far so good. Give me some time to get used to the humid weather here. Um, but now I feel comfortable now. It's not too dry especially in winter. So especially in winter, I feel much more comfortable. But in the summer, it's just a bit hard to to get used to.
Maybe. Yeah, but you will not be suffering from any cold like you used to in Michigan, so that's
Yeah, right.
Is my face is the bigger face now for everyone?
no, it looks fine. It's a slightly bigger, but um, not too big.
Yeah, it
Oh,
looks okay.
yeah, yeah, it is.
Okay.
It is.
I think
Mm.
it's only me and the committee are allowed to start a video, so it's not a big deal. It's just like I think five people, so.
Cool.
It's fine. Admitting whoever is trying to join.
There's a guy called Anis. You-
Yeah, he's a member of my family.
Okay,
Oh,
sounds great.
okay.
Is that your dad?
Uh, you mean Anis?
No,
No,
but it's
Amish.
Amish.
There's a
Amish.
yeah.
It's definitely one of the family. I don't know.
Okay.
Could be my dad, could be another Amish.
Okay, that's fine.
Yeah, it's the link has been announced like publicly, so there might be people that I don't know too.
Okay, I hope we don't get Zoom bombed. Right? Speaking of adversarial attacks, right?
Mhm.
Okay, yeah, you guys are co-host.
Yeah, I'm admitting people when I see it. So you gave me the privilege, so
Yeah, feel free to
why
admit
not use it?
people, especially after I start presenting. I'm not gonna be able to admit people.
Okay.
Did Professor D and Professor Hafiz joined yet?
I see Professor Lima. I don't see Professor Hafiz.
Oh, I need to make her a co-host so that she can unmute herself.
Okay, now I can talk.
Yeah, sorry,
Without
all
melody.
participants were unmuted by default. I'm making you all co-hosts so that you can jump anytime and share your video.
Thanks.
But I don't see Professor Hafiz yet.
Yeah, so let's give him a few minutes and see how it goes.
I have a lot of audience.
Yeah, it's I didn't know there's gonna be a large audience. I know it's public.
You are popular.
Okay.
Yeah.
So Abby, where are you now? Are you in Michigan? Or you are in California or New York? I don't know where your intern position
I'm still in
location.
I'm still in Michigan. I'm working remotely.
Oh yeah, you work remotely. Oh, that's good.
Yeah,
Yeah.
it's convenient. Oh,
Okay, I see Vinod is joining.
Vinod is here.
Cool.
Oh, Professor Malik is already here. Probably we can start. Yeah,
I don't see him.
Oh, he's here. So you
he's
just
here.
give him
Oh,
the
okay. I'll
permission.
make him a co-host and we can
Yeah,
start.
yeah. I'll just
Okay, now
introduce
finally
you.
I'm able to basically speak. Okay.
Yeah, sorry,
Sorry for
I
running
was
late.
waiting
Nice. Okay.
for everyone to join and so that I can make you all co-hosts.
Thank you.
Sounds good. Okay, so I think we can start. So I'll just do a brief introduction, and then Abe would take the floor. Okay.
Okay, sure.
All right. Thank you everybody for coming to this dissertation defense. It is indeed my pleasure to introduce Abe, who has reached the culmination of his PhD journey and is here today to defend his dissertation on multifaceted characterization and enhancement of machine learning security. Over the past 5+ years, Abe has worked hard and demonstrated an impressive combination of intellectual rigor, in my opinion, creativity, and resilience in tackling some of the most pressing challenges in machine learning security. And as an advisor who closely worked with him, I am super proud that we are here to celebrate his PhD journey. So his dissertation, as he will be talking about it in details, dives into this multifaceted nature of machine learning security, addressing vulnerabilities of machine learning across many dimensions. And I believe because this research area is pretty critical in today's context, you all know how AI is important in every aspect of our lives, where the widespread adoption of AI and machine learning is also coupled with rising adversarial threats and exploitation techniques. So his work makes solid contributions in this front. And with that, I'll leave the floor to Abe to tell us his adventure for the past 5 years in this PhD journey. Take it away, Abe.
Okay, thanks, Professor, for the introduction. I suppose you guys are seeing my screen, right?
I do.
Okay. So, hello, everyone, and welcome to my PhD dissertation defense. My name is Abderrahmen Amich, and the title of this presentation is multifaceted characterization and enhancement of machine learning security. Before I start, I'd like to thank all the members of the dissertation committee and everyone attending today for taking the time to be here, and I hope you all enjoy the presentation. So just to set the scene here, the machine learning setting considered in this work is supervised machine learning, in which we train a model on labeled training samples like malware detection, image classifiers, spam filters, and so on. And here is the typical pipeline for that, where a trained model is deployed as a prediction API that allows users to submit inputs and obtain predictions as outputs. When we talk about progress happening in machine learning, there are two sides. One side is this exciting side full of success stories where machine learning has made significant progress in predictive tasks, such as image recognition, object detection, autonomous driving, machine translation, cancer detection in healthcare. We have also seen machine learning powered games beating human professionals and machine learning powered voice assistants such as Siri and so on. All of these are great. However, my PhD has been focused on another equally important side of machine learning, which is machine learning security and trustworthiness. And the motivation is, by looking at this pipeline, we might ask the question, what could possibly go wrong? In other words, what could go wrong if we replace the user with an adversary? There are at least 4 potential threats that the pipeline will have to deal with. A widely explored and still open problem is adversarial inputs, or what is also known adversarial examples, where an adversary perturbs an input so that the model returns incorrect predictions. The perturbation here is not random. For instance, in image domain, perturbations should be visually imperceptible, while in audio domain, the perturbation needs to be inaudible. And in domains like malware detection, the perturbations needs to preserve the malicious functionality of a perturbed malware. Now, before we dive into our contributions, let's briefly summarize the main works of machine learning test time evasion that preceded this body of work. Research in this area has been drastically increased since 2014, when one of the most influential evasion attacks named fast gradient sign method has been proposed. It relied on defining a perturbation size that has the same sign as the model gradient. And later on, improved attacks have been proposed, such as the basic iterative method and the projected gradient descent method that considered multiple steps of the fast gradient sign method. And after that, researchers suggested countermeasures, mainly defensive distillation, which has been proved effective against gradient-based attacks, along with other defenses such as gradient masking. And in 2017, an optimization-based attack called Carlini-Wagner broke defensive distillation. And so far, it is still known as one of the most powerful attacks, yet not realistic, due to its high performance overhead and the assumption of white box access to the target model. In the meantime, there were various black box attacks that have been also proposed in this area. Simultaneously, other works proposed the idea of training the machine learning model on select adversarial data so that it can perform better in their attack. Adversarial training is one of the most famous defenses. However, it does not solve the problem. It also sacrifices the model's initial high accuracy on benign data. In 2019, efforts to explore uncertified defenses have emerged, hoping to offer provable guarantee of machine learning security. Although this is a promising research direction, most of the related works are not scalable and only tried on small neural networks, or they just offer a low defense certificates. In our published body of work, we aim to explore and characterize evasion attacks, advance the defense landscape, investigate the roots of machine learning security threats, and much more. So we looked at the problem from multiple views. First, we started by performing a high-resolution diagnosis of evasion attacks to boost security assessment. Then we explored the moving target defense, where the model's decision boundary moves in the face of the adversarial inputs. After that, we looked into models deployments that can generalize to benign and adversarial distribution shifts. And lately, we performed a characterization study of how neural networks activation graphs have different patterns in their attack compared to benign setting. Additionally, in another direction, we have explored the idea of using adversarial tactics for good. Now let's dig into the interesting contributions, starting by the deep diagnosis study that offered a fine-grained understanding of machine learning evasion attacks. Going beyond the attack evasion success that is usually observed by a decrease in the model's accuracy on malicious input, in this study, we investigate if there is actually a direct cause-effect link between the wrong prediction result and each feature perturbation performed by the attack. In other words, are all feature perturbations consequential to the evasion results? If not, how many are non-consequential, and how does this affect the effectiveness of the attack strategy? To this end, we use machine learning explanation methods that are initially introduced to explain why machine learning models make correct decisions. By the time we conducted this work, there was multiple explanation methods to consider, such as LIME, SHAP, and LEMNA, and these methods return the direction of each individual feature in the input sample with respect to the predicted label. For example, given this, looking at this MNIST example, SHAP explanations highlights in pink features that are directed to the true prediction 9. We call these features positive features. And in blue, it highlights few pixels that are directed to other labels. So the high density of pink here explains why the model returns 9 as a prediction. In our work, we perform explanation methods on adversarial inputs in order to highlight positive perturbations that are consequential to the evasion results from negative perturbations that are non-consequential. In few words, this work was about using the post-evasion feature directions to define a suite of aggregation metrics for correlation analysis. First, for every sample, we computed the perturbation precision, which is the ratio of consequential perturbations from the total feature perturbations made by the attack. Second, we captured the perturbation error, which is the number of perturbed features that are still directed to the correct prediction. And then we aggregated our computations over all adversarial samples to find out whether input manipulations at the granularity of each single perturbation are correlated to the evasion result. For tests and evaluation, we considered a variety of datasets. First, we started by collecting our own dataset by running Windows executables, including malware samples on Cuckoo Sandbox to extract its traces, like API calls, DLL files, and others. We additionally considered another malware dataset called Ember, which is one of the benchmarks for malware detection based on static features. Finally, we checked whether our findings can transfer to images by considering MNIST as another dataset. So this study revealed some intriguing results. First, we noticed that more than half of perturbations made by evasion attacks have a weak correlation with evasion result. And some of them are false perturbations, since they are not directed to the wrong labels. The conclusion here is that at the level of each feature perturbation, machine learning evasion attacks can make non-consequential perturbations. And the accuracy metric is not enough for security assessment. We actually need deeper fine-grained evaluation, and that's what this work offered. So this work leaves us with the main question. Is there a way to make known evasion attacks more consequential at the level of each feature perturbation? We addressed this question in another work that led into building an explanation-guided approach to ensure evasion attacks only make consequential perturbations. We used machine learning explainers on adversarial input generated using a baseline attack. Then, depending on the baseline attack's effectiveness, EG-booster acts differently. If the baseline attack perturbations already lead to evasion, then EG-booster only attempts to look for unnecessary perturbations and remove them. Otherwise, if the baseline perturbations fail to result in evasion, EG-booster not only eliminates non-consequential perturbations, but also perturbs features that are originally directed to the correct label. In this example, we show how EGBooster can further improve fast gradient sign method attack on MNIST. Initially, the fast gradient sign method fails to flip the true label 7 into wrong prediction, and then EGBooster adds consequential perturbations, which are highlighted in green, that successfully misclassifies 7 as 9. This is another example where fast gradient sign method already succeeds to evade the model. EGBooster only eliminates unnecessary perturbations that have no impact on the attack's success. As a result, EGBooster minimizes the number of perturbations, which makes the attack stealthier. To evaluate EGBooster, we started with an MNIST CNN model for proof of concept, and we considered a wide range of notable white box and black box attacks as baselines. We compared the evasion rate of each attack before and after enhancing it with EGBooster. So for fast gradient sign method and the basic iterative method, we observe a significant improvement in the evasion rate due to 14% of added consequential perturbations by EGBooster. For PGD attack, we observe similar evasion rate improvement while guiding the attack to make 4% less perturbations. EGBooster eliminates 15% of non-consequential perturbations made by the Carlini-Wagner attack, while keeping the evasion rate well above 99%. And finally, we showed that EGBooster provides the same performance on black box attacks. Next, we evaluated on CIFAR-10 as a more complex dataset, and we observed similar results to MNIST findings. What is actually more noteworthy here is that across all the studied attacks, EGBooster is detecting a significant number of unnecessary perturbations that has nothing to do with the attack success. We have also tried EGBooster in a more challenging setting, where the target model is defended with adversarial training, and we found that it can still succeed to guide all attacks towards higher evasion rate. We also tested if EGBooster inherits the lack of stability limitation of explanation methods, and we found that its performance is stable regardless of the explainer stability that we see here in red. Finally, we also tested EGBooster on different attack norms and different attack sizes and found that its performance is agnostic to the attack parameters. Now, the main takeaways here is that machine learning explanation methods can be leveraged not only to diagnose adversarial perturbations, but also to guide them into more successful attacks. EGBooster adds consequential perturbations and removes unnecessary ones to enhance baseline evasion attacks. EGBooster is found to be agnostic to dataset, model, attack threat model, attack size, and the attack norm. And it does not inherit the explanation and stability of the used machine learning explainer. Now, we switch our focus to the other side of the attack defense arms race, and we explore possible advances towards more robust machine learning models. Our investigations in this area led to building a moving target defense that we called Morphence. The motivation of this work is that a fixed model is a sitting target that blindly accepts queries, which makes it an easy target by adversaries. As a result, any defense would eventually be broken after multiple attempts, since the model is not moving between queries. Another major issue of fixed models is that the attacker can confidently repeat a previously successful attack. However, repeated attacks are not guaranteed when the model is actively moving. The idea is to make the pipeline like this. Given an input, a new different model is selected for the classification task. As a result, if one malicious query evades the selected model, it won't necessarily evade it again, since another model will be selected for the next query. Additionally, probing-based attacks that requires multiple iterations to perform perturbations will face a new different model for each iteration. which makes it more difficult to converge to evasion. Now let's talk about the main steps to realize Morphence. First, we start by training a base model that plays the role of a teacher model. Then, by performing small different randomized perturbations on the model weights, we obtain n new different student models. So naturally, these models are less accurate than the original model. So we retrain them to regain their accuracy. And in order to increase the diversity of these models, we use n different training sets by performing different transformations on the original set. This final measure plays a major role to reduce attack transferability between the n models. So at this point, we have n different models ready for accurate classification. However, each single one of them is not defended against adversarial examples. Therefore, to add adversarial awareness in the pool of models, we perform adversarial training on each model using its previously transformed dataset. However, we know that adversarial training has a limitation to sacrifice accuracy on benign data. Therefore, to mitigate that limitation, we keep a subset of the n models undefended. And for adversarial training, we consider a mixture of attacks to increase the model's generalization over attacks. And once we have a new batch of n models, we add them to a stack that locally store previously generated models. Meanwhile, the model generation process keeps running locally as long as Morphence is deployed in order to prepare for backup batches of models. Then, a batch of models is selected from the stack for deployment, and when the user sends a query, each model suggests a prediction with some confidence. The model with the highest confidence is selected to respond to the query. And to maintain the moving target aspect of Morphence, a seamless update of the deployed batch is actively performed once the number of queries reaches a query budget Qmax. The Qmax variable is predefined in a way that it satisfies the condition that the currently deployed batch of models can be renewed if and only if the time to generate at least one other batch has passed. Therefore, at the time of renewal, we ensure that the stack is not empty. The goal here is to avoid any potential denial of service attack that targets models availability. So we start with MNIST evaluations. We track the accuracy of baseline CNN model before and after attack, also when adversarially trained versus when deployed with Morphence defense. Under no attack, Morphence has a comparable accuracy to the baseline model, while adversarial training causes around 3% drop in accuracy. On fast gradient sign method, Morphence significantly improves the accuracy compared to adversarial training, while adversarial training is useless against Carlini-Wagner, Morphence succeeds to remain the accuracy around 97%. We also considered SPSA as an iterative probing-based black box approach that uses multiple queries to identify perturbations, and we found that Morphence is more robust against SPSA than adversarial training, which shows the impact of the moving model aspect. Additionally, we evaluated Morphence on CFAR10 as a more complex and realistic dataset, and we observed similar results as Morphence still drastically improves robustness and overcomes adversarial training. In another experiment, we explored in the impact of Morphence model movement in avoiding falling to the same attack multiple times. The following figure shows that attacks that are successful on the first pool of models does not necessarily remain successful on the ulterior batches, which shows the direct impact of the model pool renewal step performed by Morphence. Now, the takeaways here are: a moving target model is more robust than the best fixed model. A moving target model can prevent falling in the same attack multiple times. And iteratively probing a moving target model is not effective to optimize adversarial perturbations. Now, despite all these significant advances made by Morphence, till now, it is still not clear why machine learning models are vulnerable to adversarial examples. And to address this question, we looked into whether machine learning out-of-distribution generalization problem can be a direct cause that makes machine learning models struggle to generalize on adversarial examples. In this work, we actually confirmed the cause-effect link between... Yes.
Maybe it's time to check with the committee members if there are any questions, because you've covered enough ground to pause for a question for a moment, maybe.
Sure, yeah. Is there any questions?
Any questions from the committee members?
I do have one quick question. Dr. Ma, you can go ahead.
Oh, yeah, I have a very quick question. So for your EG booster, so you mentioned it's not very relevant to the explanation stability. So can you explain a little bit more, because I'm not in that field? Try to understand how the evasion rate is related to the explanation method you are using.
So in terms of stability, the explanation methods showed that they can be unstable, like between different runs. If you run like an explanation methods on the same model with the same characteristics, sometimes the explanation weights can be different from one run to another because most of these approaches are non-deterministic. So since we used them in EG Booster, we wanted to see if EG Booster would inherit that instability. And we found that it does not inherit that instability.
Okay, good. Thanks.
Can you go back a few slides? Keep going. I'll let you know where to stop because I didn't see the slide number. So that's why. Keep going back, please. Keep going. Keep going. Yeah.
This one?
No, keep going. I'll let you know where to stop. I think it was the previous stack of slides. So keep going, please.
Is it
Yeah. So yeah, this is like basically very interesting work that you have done here. If we have, we know what the general target is. For an attack from attacker standpoint, and like a selective or effective perturbation that you guys are introducing, and investigating what are relevant and what are not relevant, unnecessary kind of perturbations. So in this case, like the thing is, I would like to know your thoughts on basically. If we know that a given input model, a given trained model for a given object, a given like a class, if we know, for example, 7 can be mistaken by or like mapped to or wrongly classified to 9 or maybe 8, but 2 maybe also. But the thing is, the set is relatively smaller. So I would like to know if we have the knowledge, hey, this model can be potentially be translated into this model. You see what I'm saying? Or I need to explain it further. So what I'm saying is 7 can, it's very difficult to misclassify 7 as 0. Compared to 7
that's actually doable. There are another class of attacks called targeted attacks. So these targeted attacks, you give the target label that you're interested in, for example, 0, and the attack will make perturbations in order to make sure that the model misclassifies, for example, 7 as 0. Those are
0. So you know the target. Okay, I got it. So in this case, basically targeted attacks. So how did you evaluate the performance of your AG booster, your algorithm for targeted attacks? Is your model or your system still you can say suggest or implement or incorporate smaller number of perturbations? Did you test that thing also or not yet?
Yes, it does. It's actually the as we've shown before, EG Booster is agnostic to the attack that we're using, whether targeted or untargeted. So what it does is basically
Mhm. So you have data for that targeted and untargeted?
no, we didn't focus specifically on
Mhm.
categories, but
Okay.
EG Booster, like conceptually speaking, it would work on both because it basically takes the perturbations that have been made by the baseline attack, whether it is targeted or untargeted, and looks for perturbations that are non-consequential using explanation methods.
Mhm.
And if they're not consequential, we can just eliminate them. They're not going to impact the final result, whether it is targeted or untargeted attacks. And it can also add consequential perturbations. For example, if you want to change 7 to 0, and there are perturbations or let's say pixels that are more relevant to the prediction 0, EG Booster will identify those and make perturbations at the level of those pixels.
Okay, understood. Go to this moving target attacks that you have, basically training multiple models, then randomly picking one of these models. So in this case, basically what strategy is typically used in this moving model strategy? How you pick a given, because all of these models are equally efficient, but still would like to know how you would pick a model.
Yeah, that's actually a great question because that was one of the challenges that we faced when we were developing Morphence. And there are actually two versions of Morphence. When I come back to the presentation, I will talk to Morphence 2.0. In Morphence 2 1.0 that I presented, we used model confidence. So we have this batch of models. Each model has a prediction for an input, and it has with a certain confidence. So the selection happens. The scheduling happens by selecting the model that is most highly confident with the prediction. It's not the most efficient way, but at this moment, that's the best thing we can do. But later on, I will show how that scheduling approach improved a lot.
So you want to keep that as a secret for the moment. Okay, I understand. So I would like to have your thoughts on another thing. We have a multi-agent approach typically, which is a substitute to this one or similar to that one. So you have multi-agent approach. So your thoughts on that one, using multi-agent approach versus basically this, whatever the strategy you use, like confidence-based or some basically a most recent performance-based selection. So your thoughts on that?
Can you explain what do you mean by
what I'm saying is you have the multi-agent approach. So basically what happens is you have multiple agents, multiple models. Each agent is a model. We have multiple models, and then you have a controller agent, which is a controller model that basically pick one of those models. Okay, and you produce the output. Okay, we are also working in this space also, and sometimes you have basically some kind of average of everybody, get the result more or less at the same level,
some kind of
what I'm saying, basically, let's suppose you have, in this case, you have 6 models. So random selection, basically 1/6 of each weight you use, and then you assign the, label that you are going to get at the output, or you use the majority voting or some kind of basically model output fusion kind of approach. Okay. So if you don't reveal your selection strategy okay, or your weighting strategy, then the attacker would probably not know quickly what basically which model is contributing at the output in that case. So what I'm saying is your thoughts on strategy that you are currently using versus multi-agent based approach with fusion strategy.
Multi-agent versus fusion?
No, I'm saying multi-agent based output fusion strategy.
What is the question exactly with respect to that?
The question is you are using one strategy here, you pick one of the model that
we actually tried two. We tried the highest confidence and majority vote. Majority vote is not suitable in this case because the pool of models has adversarially trained models that are not performant on benign data, and there are other independent models that are accurate on benign data. So if for each input, regardless of whether it is benign or adversarial, all models have vote, the limitation of adversarial training will impact the overall accuracy of the whole system. That's why majority vote, we tried it. Conceptually, it's not suitable. And also when we tried it, it's highest confidence is better. I don't know if that answers the question, but I think you were talking about something about fusion or something like that.
Fusion, basically, you have the models because the thing is, you already answered the question partly by saying that they are adversely a model trained on adversarial data, and therefore their output are going to be in a way that the fusion strategy might not produce the best results. That's what I understood, and I think that's fair enough. Yeah, that's good. Thank you.
I think the best scheduling approach here is to somehow find a way to attribute benign samples to independent models and adversarial samples to adversarially trained models. And that's actually what we done later on in Morphence.
Okay. So you reveal your secret.
Yeah.
Yeah, okay. Yeah, my question is pretty similar to, it's correlated to Hafiz's question. I think that's probably one your this morphing model really work like a mixture of expert idea that you have different experts say that you have 4 models and you have probably 4 experts that target a different type of specific thing, and now it works together to solve a problem. Here you just pick one model, or you especially train one model to perform one task. Then I feel the idea is probably the same, but additional thing that probably is relevant to these is in the mixture of experts setting, there is couple of options. There are a couple of options to direct your samples to experts, to multiple, one or more experts. Say that you have multiple 4 agents, maybe you want to pick 2 because it's a kind of a combined attack, or the case is a little bit complicated or unseen. Then how do you target that?
So you mean when 2 models
let's say
have the same confidence?
Yeah, maybe some combined attack that you never see in your data set, in your training data set. Then just picking up one model, will that work? I feel that is highly relevant to Hafiz's question, that some data, some attack you never see, it's a kind of fusion of attack or complex attack.
That's actually why we need the moving target model. Like we could have just performed adversarial training, and like you said, you can't perform adversarial training on all the attacks out there. There could be some data that the model hasn't seen before. That's why we introduced the moving target. It's first to make the attacker's life harder, because most attacks, whether they are optimization based or multiple iterations, they are based on querying the model multiple times to decide what are the suitable perturbations for that specific model. So if that model is moving from one query to another, finding the right perturbations are harder, because once you get a feedback on one model, you try to use that feedback, you will get a new model that is totally different. So that's why we have the moving target aspect. That's why we actively change the batch of models. And the scheduling approach that we talked about is just to make sure that we don't sacrifice accuracy on benign data while we're doing that.
Okay, thank you.
All right. I think we can move on.
Yeah,
If
thank
you
you for the questions.
Yeah.
Let's. Yeah, we stopped here, right?
Yes, go ahead.
Yeah. Okay. So in the previous slide, we were talking about, despite all these significant advances made by Morphence, it is still not clear why machine learning models are vulnerable to adversarial examples. And we addressed this question. We looked whether, by looking whether machine learning out of distribution generalization could be one of those causes. And we actually found the cause-effect link between both problems. So the main motivation is that machine learning models are by design trained to generalize on unseen identically distributed data, which makes them perform poorly on out-of-distribution test inputs. And in this regard, we argue that adversarial perturbations lead to adversarial distribution shifts, which might make adversarial examples another form of OOD data. So to verify this intuition, we used one of the recent benchmarks in OOD detection called SSD on adversarial input. And results on CIFAR-10 showed that most fast gradient sign method and PGD inputs were detected as OOD. And a direct implication of these results is that OOD detectors can be repurposed to be used for adversarial example detection. And for Morphence 2.0 that we talked about earlier, we leveraged this idea to extend Morphence into more effective scheduling. Instead of just selecting the most confidence model, we used an adapted version of SSD to decide whether a user input is suspect to be adversarial or not. And in this example, since the input is benign, it is assigned to the most confident model from the set of models that are not adversarially trained. Now the secret is revealed, but this
Okay.
actually
So
led to, yeah,
here I just quick question.
sure.
How would you know that this input is non-adversarial? I mean, what strategy are you using? The previous slide.
Adversarial example detector.
Oh, okay. So that's a separate, like basically, or
Yeah.
within the system it's integrated, or it's a separate?
Yeah, let's go back to the previous slide. So you see this.
Yeah.
This is a detector that is used as a proxy here to detect whether the input could be adversarial or not. And the intuition is that adversarial examples are also considered as out of distribution examples because the model has no idea of the distribution of that data. So we kind of leveraged out of distribution detectors and we repurposed them for adversarial example detection. And that's how we added a detector there.
Okay. Okay.
So is this a detector? So is this a detector another neural network or is some rule-based detector?
It's another model.
It's another learning model.
Yeah, it's another learning model. It's called SSD. I think it's not like a typical classification model. It's more of using some self-sufficient learning, and that's how it did. So the idea is to make the model learn the distribution of the training data so that it can detect any out of distribution samples, including adversarial examples.
Okay.
But it's not our work, the detector. It's work called SSD that has been previously proposed, and we just repurpose it for this work.
Okay, appreciate.
Okay. So adding this model actually led to a more effective scheduling in terms of assigning adversarial input to adversarially trained models and benign ones to independent models. Now, apart from Morphence and following the same motivation that adversarial examples are out of distribution, we explored another approach that can generalize machine learning models not only on adversarial examples, but also on naturally induced distribution shifts. For that, we use distribution mapping methods as a proxy. This tool is called out to in, and the idea is if an input is detected as OOD, it is delivered to an image-to-image translation model that converts the input to the distribution that the deployed machine learning model has learned. In this figure, we show visual examples of how image-to-image translation methods can map adversarial examples to the benign distribution on 3 different data sets. Here, we used 2 different translation methods called pix-to-pix and CycleGAN. And in addition to the single translator approach, we have also explored the use of ensemble of translators. The idea here is to cover more possible distributions of inputs, since the input distribution is unknown in practice. So the image-to-image translation methods adopted in this work are pix-to-pix and CycleGAN, which are both different generative adversarial network architectures. Pix-to-pix is a conditional GAN that has 1 generator and 1 discriminator. So given an input from distribution A, which is the source distribution, the generator would propose a translation in B, which is the destination distribution, and the discriminator is trained to decide whether it is fake or real. Pix-to-pix requires a paired training set where every sample from the source distribution A must have a counterpart in the distribution B. On the other hand, CycleGAN is a more complex architecture that introduces 2 GANs to be trained at the same time by cycle consistency loss, which makes it capable to be trained on an unpaired dataset. The first GAN of CycleGAN has a generator that translates an input from A to B, and the second GAN is trained to reproduce the original sample by translating the result back to A. And that's how the cycle is realized. We compared our approach against state-of-the-art defenses, mainly adversarial training and ensemble adversarial training, on 3 datasets of different scales. And focusing on the highlighted numbers, we observe that out to in led to impressive results in terms of robustness against evasion attacks on MNIST, and it significantly increased the robustness of machine learning on CIFAR10 and ImageNet. Also, unlike adversarial training techniques, it does not sacrifice accuracy on benign data. And in addition to a variety of standalone translators that we considered here, we have also tried ensemble translators, and the results show that ensemble translator is more likely to reach best results. We have also tested out to in on natural OOD input, such as darker or sharper images. In the table, we find that out to in can make the model generalize on these OOD samples without the need to retrain it. The takeaways here is that adversarial perturbations cause distribution shifts, which is there a question?
I don't hear any.
Okay, I heard some echo. So the takeaways here is that adversarial perturbations cause distribution shift, which is one of the major reasons of machine learning evasion. Our approach highlighted the utility of image-to-image translation to generalize machine learning systems on OOD data, including adversarial examples. Also, we showed that mapping different types of input to the training distribution could be the answer to deploy more reliable and secure machine learning system. And unlike adversarial training techniques, out to in preserves the exact accuracy on benign data, while significantly increasing robustness and generalization on OOD data. So moving on, in this body of work, we were also interested in unpacking semantics of DNNs in adversarial settings. To that end, we explored a behavioral characterization approach via the inference activation graphs. More precisely, given an adversarial input, we wanted to check if we can distinguish an activation pattern of the DNN compared to its normal behavior on benign data. For that, we explored in the inference activation graph of the model, which is basically the graph representation of the model, composed of its multiple layers. What we wanted here is to capture possible strange behavior in the model's graph when it is under attack. For instance, is there any strange pattern in terms of the activation values of each node, or the number of activated nodes, or the activation frequency of some specific nodes? Additionally, what if we can identify some specific nodes that are activated only on adversarial inputs? We can call those adversarial nodes. In addition to these empirical investigations, we explored a more systematic approach by leveraging AI to learn to differentiate between graphs of benign versus adversarial inputs. Then we performed node attribution on the resulting model using machine learning explainers to search for nodes that are highly attributed in benign setting, which are colored in green, or nodes that are highly attributed in adversarial setting, colored in red, or just nodes that are generally highly attributed regardless of the nature of the input. These also could be useful, and they are colored in dark blue here. We tested this approach on CIFAR-10 as an image classification system using a ResNet 18 model and Ember as a malware classification system using a dense neural network. At the level of each layer, we captured the range of the recorded values for each node in benign and adversarial settings. And as we show in the figures, we can clearly find distinction between benign and adversarial settings for both models, suggesting a different activation behavior when the model is under attack. Now the question here, is there a way to use this information to improve the model robustness? To do that, we would aim to maintain the same benign activation pattern when the model is under attack. For that, we can start by nullifying nodes that are activated only in adversarial settings. And for the remaining nodes, we can try to bring the activation values closer to their range in benign settings, starting by nodes that are highly attributed because they are more important in the inference. Now, in order to identify the best order of actions, we follow an action enforcement method by keeping track of the cumulative gain and loss in accuracy after each tested node level action. And to do that, we capture the trade-off in accuracy gain under attack and accuracy loss in benign setting after each tested action. This is an example where we show how we identified robustness enhancement action for Ember on the first layer of the model. In the initial iteration, we proceed sequentially through the nodes, following their natural order. Next, we identify the actions that lead to drops in accuracy and cumulative trade-off to remove them from the current iteration, retaining only the effective ones. Then, we reintroduce them in the next iteration to determine if any of them can provide a positive impact. This process is repeated until the cumulative trade-off begins to stabilize with no further observable increases, which is what we see in the figure on the right. Another important observation in these figures is that just by acting on one layer of the model, the accuracy under attack jumped from 55% to 73%. And these are the final results after performing the same method on all layers. We observe more increase in the accuracy under different evasion attacks for both considered models. The main takeaways here is that neural networks can exhibit different activation patterns when the input is an adversarial example. Also, the inference activation graph can be effectively leveraged to identify node-level actions for robustness enhancement, and this is regardless of the studied system. So, in addition to the large body of research in this area, our multifaceted approach towards machine learning security has led to a deeper understanding of the problem and the significant mitigation of attacks. However, till now, there is no solution that completely solves the adversarial example problem. As a result, recent research has been more oriented into accepting the inevitable existence of adversarial examples as a machine learning security threat, while just trying to rely on mitigation methods and the usage of large, diverse data sets. So something intriguing in this context is that what if we can leverage adversarial examples for good? I mean, would there be cases where it would be in our benefit to evade the machine learning model? The answer is yes. And here is a real-world example. So we all know that there are a lot of internet censorship around the world, especially in censored regimes. These censors serve as middle boxes to cut the connection between an internet user and the forbidden server or a censored website. And there are several censorship circumvention tools that have been deployed to automatically probe the censor with packet manipulation strategies in order to identify manipulations that can successfully evade censorship. The problem here is that the repetitive probing of the sensor can be detected on the sensor side with machine learning techniques. Therefore, the user can be identified and possibly punished for trying to evade censorship. In this case, it is in our benefit to evade the machine learning detection on the sensor side by trying to craft adversarial stealthy probing. So first, to show how machine learning can be used by the sensors to catch internet freedom users, we look at network traces and notice that packet manipulations for censorship evasion can cause strange behavior such as overlapping TCP segments, corrupt data offset fields, and invalid TCP flags. And relying on these distinguished features, classic machine learning classifiers can accurately detect network flows that incorporate packet manipulations. Furthermore, we found that using these flow-level detections as sequential observations for hypothesis testing can lead to an IP-level detection of users trying to evade censorship. So given this detection threat, it would be beneficial for internet freedom researchers to evade such machine learning-based detection system. Inspired by adversarial examples for machine learning evasion, we propose deresistor to protect internet users from sensor-side detection. The idea is to make the user's packet resemble more, to some extent, to normal network activities. In this figure, we highlight the impact of deresistor in toning down the detectable features that we explored earlier. So to do that, deresistor introduces systematic pauses on the repetitive sensor probing and waits for the user's normal internet activities to reach a pre-selected number of normal flows. As we showed before, without deresistor, the sensor can catch the user after 2 manipulation attempts. So deresistor would stop sending manipulated packets and switch to normal traffic. Then, adding 1 normal flow will drive away the detection likelihood and delays the hypothesis testing convergence, which makes it safe to try another sensor probing flow. And following the same approach as we move forward, the likelihood value will be trapped between the 2 thresholds used for hypothesis testing. As a result, the sensor probing phase can be completed in a detection-resilient manner. We tested deresistor in 3 censoring countries, China, India, and Kazakhstan, and we assume that each sensor is deploying the machine learning plus hypothesis testing detection approach. And in the 3 countries, and for the 5 vantage points, we found that D-resistor can bypass IP level detection and reduce flow level detection while maintaining the ability to evade censorship. Okay, so let's summarize. These are the main outcomes of my entire PhD. So first, we showed in early works that robustness evaluation of machine learning models require deep diagnosis of its performance against adversarial feature perturbations. And for that, we proposed a suite of explanation-guided metrics. We also revealed that the state-of-the-art machine learning evasion attacks performs many non-consequential feature perturbations that not only make the attack less time efficient, but also reduce its effectiveness. For that, we proposed EG Booster, an attacker booster that enables only consequential perturbations. Additionally, we proposed a moving target defense to avoid repeated and multi-steps evasion attacks. Then we showed that adversarial examples are also OOD, and we proposed out to in that helps machine learning models to be more accurate on out of distribution and adversarial data. After that, we investigated in behavioral characterizations of DNNs via their inference activation graphs to understand their patterns in different security settings. This work showed promising directions into new ways to find security enhancement actions on a pre-trained DNN. And last but not least, we showed that adversarial examples can be repurposed for a good cause, and we used internet freedom and anti-censorship as a case study for that. I would like to note that most of the source code and artifacts related to this presentation are publicly available and can be found through these GitHub links. Now, before we conclude, as a future direction in this field, I think we should prioritize the security of foundation models. AI and tech industries are racing to develop advanced foundation models, but the rise of powerful LLMs like GPT, Llama, and Google Gemini poses security risks. These models can be tricked through prompt manipulation, leading to data leaks, policy breaches, and responses to unethical requests. Additionally, they often display bias in sensitive topics. Also, as AI capabilities grow, explainable AI must keep pace to enhance transparency and build the trust in AI systems. Now, as I wrap up this presentation and with it my PhD journey, I want to take a moment to express my gratitude to some very special people. First, I would like to thank my parents and family for their love and unwavering support. Also, a big thank you to my advisor, Professor Berhanu, for his guidance and mentorship. He was there through every challenge and milestones, and I truly appreciate his support. A special thanks goes to Dr. Vinod Yagneswaner, who has sparked the early steps of one of my most significant projects during my internship at Stanford Research Institute. I'm also grateful to Professor Dima and Kimberly, whose logistical support made this journey much smoother. Their help was crucial in getting things done. Finally, a huge thanks to all my collaborators, colleagues, and everyone who contributed, even in the smallest way, to the success of my PhD. And of course, I thank again all the members of the dissertation committee who have witnessed and helped in shaping my work throughout the years. And this is the end of the presentation. I'm happy to receive any additional questions.
Okay, wonderful. Thank you, Eb, for giving us a highlight of what you've been doing for the past 5 years. And now is the time for the committee members to ask more questions. And once the committee members are done, we will also open the floor for others in the audience.
I have a quick question. Abderrahmen, you just mentioned method D-resistor. So my question is what if the same method is applied to basically your system that you have developed? I think it was the out to in. Okay, the model. No, I think before that. where you have the detector in front of, like basically where you're detecting the adversarial examples before you're selecting. I think that's a Morphine 2, I guess. Yeah,
Morphence 2?
2.0.
2.
So what if that strategy, the one that you just proposed, is applied over there?
That's doable because in Morphence 2.0, the goal was to defend the base model, not to defend the detector. But an adversary cannot do both. They cannot attack the base model and attack the detector at the same time. If they want to evade detection, the sample won't be adversarial for the base model. So the adversary has to pick one.
Okay. Okay. That's right. Thank you. I got no further question. Good work. Thank you.
Okay, Abderrahmen, I have two questions. Thanks. So first, thanks for your good presentation. The two questions. The first is regarding your last project that you showed that how we counter the censorship, and does the jump size if affect your result? How did you observe any difference if you change the jump size or anything?
You mean
Your jump size is some number, some sign called J, some symbol called J, and J
yeah.
equals 1, right?
Yeah, the jump size is basically the number of normal flows that we wait for until we get back to sensor probing. We use J equal 1, and it was effective to just use J equal 1. But there are actually more to that work that I didn't focus on in this presentation because it's out of the scope of the PhD topic. We actually tried higher jump sizes. We tried multiple adaptive attacks that, for example, we tried things against a sensor that tries to filter out normal traffic from the resistor. We tried something against a sensor that tries to retrain their detection model on the resistor traces. These are all adaptive attacks that we tried and we overcome. And we even tried using a totally different machine learning detection approach based on using LSTM model to make the decision based on sequential observations instead of using hypothesis testing. And that's also something that we found a way to overcome. So there are actually multiple configurations of the resistor to overcome these adaptive attacks. But in this presentation, I didn't want to dive into that because we don't have time and it's out of the scope of machine learning security.
I see. So basically, because we don't know what a censorship looks like, it's a black box. So you are kind of trying to debunk a black box model, and hypothesis test is just one way you make a hypothesis to the censorship model. So there could be something like LSTM model or some model. Then
Yeah.
there, okay. Another thing is
Okay.
a hypothesis you made based on the adversarial example. Your basic assumption as a hypothesis is the adversarial examples are OOD. Did you do any basic preliminary study to have that verification or justification of this hypothesis that like very subtle adversarial attack or manipulation on the data is OOD? Did you do that
Yes.
statistical test or something like that?
Yes, we did. That was in one slide in that project when I talked about it. So the slide was about using SSD, which is an OOD detector, on adversarial data, and typically fast gradient sign method and projected gradient descent data on CIFAR10. And we found that I think it was 90% of fast gradient sign method and around 87% of PGD data were detected as OOD. And that's how we confirmed that intuition and we built on it. And actually, during the revision process with reviewers and so on, we found that we were not also the first people to have that intuition. There are other works that also showed that adversarial examples are related to the OOD problem, but of course they used it for other stuff, not for the same defense that we proposed there.
Okay, got you. Appreciate it.
You're
I don't
welcome.
have other question. Professor Jinlu just asked the first question of Professor Jinlu just asked the same question as me.
Good. Should we take questions from the audience?
Yeah, so I made sure that any member of the audience can unmute themselves to ask questions. So if you have any questions, feel free to unmute yourself and ask.
I think there is also chat if they
Yeah,
can.
you can type in the chat as well if that works better. But yeah, feel free to unmute yourself and ask. I'll give you a moment.
I have a
Can
question.
you?
Yeah.
Okay.
There was
Hello.
somebody. Yeah, go ahead.
Go ahead.
Hi, Abe. Congrats for your defense. This is Firas.
Thank you.
Under. Hi. So for Morphence, you said that it's a moving target, but the attack that you generated, which model have you used to generate those attacks? Did you implement kind of framework that for whatever given attack, black box or white box? Which model have you selected to use this kind of perturbation?
So for white box attacks, we assume that the attacker has access to the base model. So for example, fast gradient sign method or any other white box attacks, it was performed on the base model because you can't perform them on like a moving target model. For black box attack, the assumption is that we perform them directly to the moving target model, to the EPI, because that's doable in black box models.
I see. Thank you.
You're welcome.
Is there another question? Okay, it seems like there are no further questions. In that case, I think we would like to thank everybody who attended, and the committee has to discuss or deliberate on the presentation and the dissertation as a whole. So we'll kindly ask you guys to excuse yourselves. That includes Abe as well. I will call you back on Slack, Abe, once we're done. Yeah, thank you, everybody.
Great. Sounds good. Thank you.